Okay. Good evening, everyone. I think please find your seats and we'll get started. My name is Fadil Santosa. I'm the director of the IMA, Institute for Mathematics and its Application. And it's a great pleasure to welcome Albert-László Barabási. I think he's one of the most original and influential thinkers of our time. László received his PhD in physics from Boston University in 1994. He held a postdoctoral position at IBM Watson's Research Center for 1 year before joining the faculty at the University of Notre Dame. There he rapidly rose through the ranks, and at the age of 32, which is when I think I landed my first job, he was named the Emil Hoffman Professor, chaired professorship in physics. He founded the Center for Complex Network Research at Notre Dame, and since 2007, he's Distinguished Professor and Director of the Center for Network Science at Northeastern University in Boston. He's also affiliated with the Harvard Medical School. Professor Barabási is well known for his work in network theory. His scientific contributions, he was elected Fellow of the American Physical Society. He was awarded the John von Neumann Medal by the John von Neumann Computer Society. He was elected member of the Hungarian Academy of Sciences and Academia Europaea. He's author of the bestseller, Linked: How Everything is Connected to Everything Else and What It Means. And he's in the news a lot. This month, he's been in the news for his prediction about smartphones. So for those of you who have smartphones, you should pay particular attention. László predicts that as more people use smartphones, not only are you going to be vulnerable to virus attacks, you will also help in spreading them. So the phenomenon that he's going to describe is called percolation threshold, and it's something that he'll talk about tonight. So please join me for a warm welcome to Professor Barabási.
Thanks, and thank you for the opportunity of being here. Can everybody hear me in the back? Is everything all right there? Yeah. Perfect, thank you. All right, so let's get to business essentially and talk about networks. And there are lots of networks out there. And the network that everybody knows is the internet. What is the internet? The internet is a bunch of computers connected by wires that allow us to spread the message from your computer to any other computer in the world. And it is happening through this network how the messages are passing from computer to computer. And this is what you see on this particular slide. You see the schematic picture of the internet, where this is where your computer is and how it connects to a router. And whenever you send the message, it goes to a router, to another router, yet another router, and so on, and ends up at the end. Now, the beauty of the internet, of course, is that it allows all these different types of computers to be interconnected. And we will come back to its structure. This is a map of the internet, and we'll talk about that as we move along. But the internet is not the only network that is out there that we care about. We are all part of a network, which is the social network that we are part of. That is whom we know, who are our friends, whom are our associates, who are the family members. What you see in this picture is a kind of a subset of that particular social network, is an example for that, which shows who is talking with who in a particular company. So this is a not too large size company, it's a medium sized company. Each node corresponds to an individual, and two individuals are connected if they regularly communicate by email or by phone, which indicates that they actually know each other. But you can do a similar experiment in schools, you can do similar experiments in neighborhoods, asking simply who knows whom, and if you do that for many, many people, you get a map of the social network. And that social network is very crucial for many, many different things, such as spreading ideas or spreading diseases, as we'll see a bit later, such as the flu epidemic that we have right now. And so that's yet another example of a network. And let me give a third network, which is within us. Each of us carries a very, very complicated network within ourselves, because we all know essentially that within the cell we have what we call genes. But the main role of the genes never really work alone. They interact with each other. There's lots of what we call gene-gene interactions. And one of the big surprises of what we call the Human Genome Project was that that we have much fewer genes than what we originally expected. What do I mean by that? Well, biologists have actually estimated, or have counted how many genes simple organisms have. So for example, the fruit fly has about 10,000 genes approximately. And when it came to humans, people were guessing, how many would we have? We are so much more complicated than the fruit fly. And so the estimates were somewhere in 100,000 and higher than that. So when the data came out, turns out that we have only about 25,000, less than 30. So the question is, how can we be so much more advanced than a fruit fly and yet only have twice as many genes? And so there is not a simple answer to this question, but before I would get to the answer, I should mention that the number of genes doesn't really matter how complicated or how advanced you are. For example, the onion has 40,000 genes, which is twice as many as humans. Yet, unless there's some hidden intelligence of the onion that we don't know of, really, the number of genes and intelligence don't really correlate with each other. So given that, what does it really matter? So what does it matter how many genes we have? And what biologists are more and more telling us is that it's not the number of genes, but the connections between them, how the genes interact with each other. And I will see some examples as we will move along. So, if you want to think about what's in your cell, there are a bunch of genes that interact in some complicated fashion with each other. And, the examples that I showed you so far, the internet, the society, and the cell, are examples of what we call complex systems. That is, they're very, very complicated. They are made of many different types of components that significantly differ from each other. You and I are very different, and among each other, you are actually very different, and yet we are all part of a social network. And we are part of this very complicated system that we call the society, and we interact with each other. And this is an example of a very complex or complicated system. But behind each of these complex systems, there's a network. So that tells us how the pieces connect to each other. And the goal of today's lecture is to talk about this network and understand how this network looks like and what does it really mean, for understanding these complicated systems. Now, whenever it comes to any complicated network, we need to go back in time and start talking about what do we expect? How should these real networks look like? If I look at who knows whom in a school, who knows whom in the university, how the internet computers are connected to each other. And the basic hypothesis in this context was formulated in 1960 by two Hungarian mathematicians, Paul Erdős and Alfred Rényi. Now, I don't know how many of you have heard of Paul Erdős. He was a really original mathematician whose lifestyle was completely devoted to math, to the degree that he would really live out of a suitcase. And he would go from university to university, from colleague to colleague, and he would show up at somebody's doorstep, typically a mathematician. He would say, my brain is open, let's prove some theorems. And he would stay for about 5 days with that host, about the amount of time it took to completely wear them down, and then he would take his suitcase and move to somebody else. So during his life, he just traveled from place to place and actually proved theorems. And he had actually a very special language for everything. For example, he called kids epsilons because that's the sign of a tiny thing in mathematics. So, for example, I was for many years a faculty at the University of Notre Dame, and Paul Erdős had his only permanent position in the US was at Notre Dame. He was there for like 6 months, and then he had to leave. He was offered full professorship, but for whatever reason he had to leave. And many years later, they asked him, how did he like Notre Dame? And he said, that's a very nice place, but there are perhaps too many plus signs over there. So the question essentially Erdős and Rényi asked is that how do we describe a complicated network? That is, if I don't know whom you know, who are your friends, how do I describe this complicated situation that there are many people you know and there are even more people that you don't know? And how do I describe the fact that who is the person who you would actually meet? And they said, well, there is lots of randomness in whom do we meet, whom would you become friends with. So the best way to describe a network is to assume that there are people, there are nodes, and each node corresponds to a person. And we assume that people randomly meet each other, which in the language of mathematics means that I pick two nodes, and I throw a dice. And if I get a 6, I say, you guys are friends. If I don't get a 6, I say, you are not friends, and then pick any other 2 people and say, let me throw a dice again and see if you become friends. Now, if you do that for every pair of people essentially on Earth, you would end up with what we call a random network. Why random? Because I let the randomness of the dice to decide who is friends with whom. And in this little example where I have only several nodes, if I were to connect them randomly, I would end up with a network that looks like this, where some people know each other, some nodes are connected by a link, and other people do not know each other. They are not connected at all by a link. So the question that really Erdős and Rényi ask is that assuming that people really meet randomly, that nodes are connected randomly in any type of network, how would this network look like? What would be its properties? How would you characterize it? And before I go there, I would like to show a little movie which shows what happens if you take a bunch of nodes and you start randomly connecting them. And for that part comes essentially the exciting part of the talk, because we go dark. And so we start with a bunch of nodes, and then we start connecting them with a certain probability, randomly pick any. So first, nobody's connected. These are kind of people floating in space. And then people start to meet each other and become friends. And as more and more people become friends, these pairs and these paths start to show up. And eventually these paths that 2 or 3 people know each other will collapse and will start forming a network. And you see, these are kind of like short paths if you have only a few links between people, but then suddenly they start collapsing, and a large network emerges. That is, if you put enough links between people, enough people know each other, then they will start forming one network, and they are not disconnected anymore. And really, what Erdős and Rényi and the mathematics literature has done from 1960 to today is to understand this process. How does it happen once you start connecting people together, once they start meeting each other, that you go from many disconnected people to a network, to a social network or any other network? But what is important in this process is that the assumption is that networks are fundamentally random. That is, that we are connected completely randomly to each other. And let's get back the lights once more. And not with that. All right. So then, now, what is the prediction that random network theory made? Well, the one way to characterize this network is to ask how many people would have no friends, how many people would have 1, how many would have 100 friends if really people meet randomly each other. And in the case of the random network model, the prediction is that this is what we call a Poisson distribution, and let me walk you through that. So this is the number of friends like a person would have, 1, 2, 3, 7, or whatever. And this is how many people have that number of friends. And the Poisson distribution means that most people have roughly the same number of friends, and there are very, very few people who would be much more popular or much less popular than the average. So what the random network model predicted is that if people randomly meet each other, it would be a very democratic society. We would all be equal. Everybody would have approximately the same number of friends. There would be no highly popular people in the society, and there would be nobody who would be left behind that has no friends whatsoever. So the question we need to ask is this true? Are we all equal? Do all of us have the same number of friends? But there's a much more fundamental question behind that. Do we really believe that networks are connected together randomly? That is, that we really randomly make friends, and that's how the society evolves. That is, that the chemicals in our cells connect randomly. And intuitively, the answer is probably no, because the society is really something that is not random. It works. There are schools, there are churches, there are universities that bring people together, and they are not random. They are successfully doing what they have to do, and that somehow should be reflected in the structure of the network as well. So the challenge for us, if the society or any other network out there is not random, then how do we describe them? And to answer this question, we needed to find real networks that we could map out and analyze. And our choice at that time was the World Wide Web. Everybody knows the World Wide Web. The name itself says that it's a web, it's a network. But the nodes are the documents, the pages that we spend hours and hours to stare at them. And the links are the URLs, the one that you can click on and go from one page to another one, that allows to navigate the web to go from page to page. And it's a huge network. I mean, I think this number is outdated. It says there are more than 10 billion documents out there. So that is, there are many more documents than how many people are on Earth. But the truth is that now the current count is close to 1 trillion. So there is a huge number of documents out there on the World Wide Web. And the question we need to ask is that, what is its structure? How do these pages connect to each other? How do we describe this very, very complicated network? And to do that, we needed a map. We needed to know who is connected to whom on the World Wide Web. And one way you could do that is you start, for example, from the University of Minnesota web page and say, let me see, what are the pages I can go from here with one click? And you can try one by one each of them, and you go to other pages. Now you could go to those pages and say, where could I go from here? And then you could go to those, and then where you could go from there. And you can see that it will be very, very boring very, very soon. So in order to not to do it by hand, which you could do by hand, essentially, we wrote a robot, which did exactly the same thing, but automatically. It started from a web page and said, let's see where could I go from there, and then went there. And then, the only advantage of the robot that it doesn't do any better than you could do, but it does it much faster, and it never gets bored with it. So at the end of the day, what it gave us is a map, where each node corresponds to a web page, and links tell you what are the other pages you can reach with one click from there. And the question is, how many links were per web page? Really, that was the question. How connected each web page were, like Google or your web page or something else? And our expectation was that to a high degree this will be random. Why would it be random? Because all of us have different interests. I care about network theory. You may care about Britney Spears. Others may care about sumo wrestling. Yet about baseball and so on. And the links you put on your web page reflect your personal interest. But we are all different from each other, and there is no way for me to guess when I go to a web page, or randomly choose a web page, of how many links it would have and where would it connect. It would be completely random because it would reflect the person's interest. And I don't know each of you, so I don't know where you would connect. So if the World Wide Web were to be random, indeed people would kind of randomly point based on their interest, then the random network theory, the Erdős-Rényi theory, should apply. And if I count how many links each page has, I should find this kind of pointed distribution, this Poisson distribution. The surprise came when we actually looked at the data, and it was something completely different. And you don't necessarily need to understand what it means to be different, but I tell you nevertheless, because we'll show an example of what this means. We found instead of this Poisson distribution what we call a power law distribution. And the question is, what does it really mean? And to understand what the difference was, let me show you an example of a network that would be close to a random network. That would be the highway system of the United States. Each node corresponds to a city, and the links are the major highways connecting each other, these cities. Now, this is a very uniform network. What do I mean by that? Each major city on the US map has 2 or 3 highways connecting it to other cities. You don't find any major city on the US map that would have 500 highways going to it. It doesn't make any sense. You don't need to build 500 highways going into any city. But you don't find any that would have not at least one highway connecting them. So therefore, if you were to count how many cities have 1, 2, 5, or 200 highways, you would find that it's very peaked maybe around, most of them have 2 or 3, and it's hard to find cities that would have much more or much less than the average. The type of network we found on the World Wide Web, visually, it's much closer to the airline system of US, where you have many, many tiny airports and a few major hubs, and all the small airports connect to the hubs. So the major difference between the two is that there are these major hubs that are completely absent from the highway network. And this is what this power law tells us, really, that most nodes have only a few links, but there are a few nodes, however, that have a very, very large number of links. They are very, very highly connected. And these networks don't only look different, but you navigate them very differently. For example, if you were to go from East Coast to West Coast, you would go through many, many cities. when it comes to flying, you may just fly to Chicago and Chicago to the West Coast. You could actually, with 2 hops, you are there. So these networks that have these major hubs these days are called scale-free networks. The mathematical definition is that there is a power law distribution with that behind them. It's easy to remember, simply say these scale-free networks are these hub-dominated networks. There are a few major hubs that hold the whole network together, and we will see soon that these have major consequences to the way the system behaves. Now, the question comes is that, okay, we found that the World Wide Web has these major hubs, and we all know these hubs. There are Google, this Yahoo, it's Amazon, and so on, these major sites, Facebook, and MySpace, and so on, these major sites that everybody connects to and everybody knows about them. And who are the small nodes? Well, it's my web page, your web page, everybody else's web pages, essentially. We are actually the small guys compared to these big major hubs that hold the network together. But the question is it only the World Wide Web? Or could there be other networks out there that may have this particular property? And it turns out that there are, actually. And one network that was discovered soon after is the Internet. You remember I told you earlier about how the Internet looks like, but I want to emphasize, people use interchangeably the word of the Internet and World Wide Web, but they're not the same. The World Wide Web that I talked earlier is this virtual network where web pages are connected to each other, and distance doesn't matter. I can just as easily connect to a web page to China than to somebody who is next room from me. So the distance is completely irrelevant. I can easily connect anywhere. The Internet is the physical network, computers connected by cables. I can relatively easily connect to somebody next door on the Internet, but if you want to put a cable between here and China, that would be a very expensive proposition. So therefore, the Internet structure, you don't expect to have anything to do with the World Wide Web because it's completely different. Yet, in 1999, Falutzos, and Falutzos have done, these are 3 computer scientists, they're brothers, they're different universities, have done a map of the Internet, and they found that it has the same property as the World Wide Web, that is, it's dominated by the hubs. And here is a map of the Internet that I already flashed earlier. What do we see here? Each node corresponds to a router, the computer that passes the messages from computer to computer. Links tell you how these routers connect to each other. And it's kind of laid out so that it looks nice. That's kind of the only reason the way it's laid out. But if you look at the map, you see that there are a few major hubs here, and there, and then there are many, many peripheral nodes with the few links only. So indeed, this Internet has the same property as we showed earlier. It is a scale-free network. It's held together by these major hubs. Let me show another example that we care sometimes in science about, which is how scientists collaborate with each other. What does it mean, collaboration? It means that 2 or 3 scientists get together and they solve a problem together, and as a result, there is a publication, and the publication has everybody's name. Why is that important? Because then based on the publication, we can figure out who is working with whom, who knows whom. And this is called the science co-authorship network. If 2 scientists have written a paper together, then we connect them on this particular map. And so nodes are scientists, and the links means that they really work together on some problem. And you can kind of see that this has some interesting properties, but the point is that if you were to count how many links each scientist has, it turns out that, again, follows this property that most scientists have only a few collaborators, and there are a few that collaborate with hundreds. And you remember I told you about Paul Erdős that every 5 days would go to a different university to work? He is the most connected mathematician of all. He has more than 500 collaborators because, he just stayed for 5 days, proved some theorem, and moved on. And as a result, there was a joint paper based on that. And I'll skip this one. The last example, actually, is a very interesting one, and you can probably figure out what are the nodes and what are the links. And the question is, why do we care about that? Why would anybody actually map out who has, let's name it, sex with whom? And the reason, because this network is very, very important to how AIDS is spreading and other sexually transmitted diseases. So when AIDS started to become a major problem in Europe, then the Swedes have gone around and started to ask, let's figure out how this network looks like, because we need to understand where could the disease go from one person to the other person. And they ended up interviewing about 4,700 individuals, very different age groups from 18 to 74 age. And they asked each of them, how many sexual partners did you have during last year or during the lifetime? The reason you would ask both questions is that people tend to remember last year than what happened during their life. But what the surprising effect was that it turned out that most people, not surprisingly, had a few sexual partners only, but there were a few who have actually thousands. And these thousands, well, those people were the hubs of the sexual network. And the reason why these are important is because if they get infected with AIDS, they can spread very widely to other individuals. So in that respect, this turned out to be a crucial factor, and we'll talk about it later, of how AIDS or other diseases spread on the social network. Now, the question we need to ask is that why? What do we mean by why? I showed you a model that how nodes randomly connect to each other. That's a random network model. And I told you that that model predicts that these networks are very democratic, that they have, in a random network, most of us would have approximately the same number of friends. There would be no hugely popular people, and there wouldn't be anybody left behind. However, what we are finding that in real networks, that's not the case. Rather, there are a few nodes, a few individuals that have a huge number of friends, and most people have only a few friends. So the question is, what's wrong with the model that I told you earlier, and how could we account for these hubs? How could we explain them? Well, to do that, we have to go back to the random network model and ask, what's wrong with that model? And there is an assumption there, actually, that you may have not catched, but it turns out not to be correct. That is, we assume that the way we connect the nodes, the way people meet each other, is that why they do so, there are no new nodes coming into the system. That is a number of nodes fixed. You take a classroom, you start having people meet each other. Why do you do that? You don't allow new people into the classroom. So that is, we assume that the number of nodes are fixed, but in reality, that's never the case. All networks that are out there are the result of what we call a growth process. Nodes always extend by the addition of new nodes. And the best way to think about it is think about the World Wide Web. In 1991, there was only one web page. That was when the World Wide Web was created, not so long time ago, essentially. And now we have more than 1 trillion. How did we go from one page to 1 trillion? Well, one node at a time. Everybody was building their web pages, and anytime somebody built a web page, a new node appeared in the system, and with that, the web expanded, became larger. So if you want to understand how the World Wide Web looks like as a network, you need to build in this growth process, how the network is growing and expanding. And let me do just that. So I can say that I will start with a little network, and I add the new node to it. For example, this node, and I connect to the existing nodes. As if a new person would have entered the classroom, as if a new web page would have been created. But the next question is, where does the new node connect? How do I choose where to connect? Where would these red links end up? And to answer that, we can go back to the random network model who said, choose it randomly. You can choose any nodes and connect to them. But again, I would argue that that's not correct. But rather, in real networks, the new nodes have a tendency to connect to the more connected nodes. And what do I mean by that? I mentioned earlier that the World Wide Web has about 1 trillion nodes out there. How many do you know personally? A few hundred. But that's not the essential question. Which are the pages that you know? You tend to know the more connected pages. You tend to know the hubs. Everybody knows Google. Everybody knows Amazon. So when you connect your web page, you are biased towards what you know, and your knowledge is biased towards the more connected pages. This is what we call preferential attachment. And the way to model that is to assume that when a new node comes, it could connect to any other node, but it prefers to connect to the more connected nodes. And this is what we call a probabilistic rule. And the way to express it is that the likelihood that I will connect to a certain node is proportional to how many links it already has. For example, I could connect to that node, or I could connect to that node. But I'm twice as likely to connect to that than to that because this has 4 links and this has only 2. One way to think about that, if this person has 4 friends and this one has only 2, this has twice as more likelihood that somebody will introduce a new friend to them because he has many more friends. There are more people to introduce people to them. This guy, somebody who doesn't have any friends, will never be introduced to a new person because there's nobody to introduce him to anybody. So really, more friends you have, more likely that you will gain new friends. And that's what we call preferential attachment. And let's see what happens if we grow a network with this preferential attachment rule. So we start with 3 nodes, and we always keep adding new nodes. And the size of the node would correspond to how many links it has, how many friends it has. And you will see that as the network is expanding, a few nodes will start growing bigger and bigger. They become really fat. And the reason for that is because there's a rich get richer mechanism in the system. If you have many friends, as the new nodes come in, new people come into the town, you know, they're much more likely to be introduced to you because there are so many people who can do that to you. So this rich gets richer mechanism is the one which is responsible for the emergence of these hubs. And you know, if you kind of run a system like that, you will find that indeed has this power law distribution, but eventually the hubs will naturally emerge. Now, I'll skip this slide, and then let's go to one important prediction of this model. What the model predicts is that as the network is growing, each node will increase the number of links it has, the number of friends it has, with the square root of time. So this is a particular prediction, but it has a very important consequence. Since everybody is increasing the number of friends at the same rate, it's always the first who came in the system who will become the hub. Because, you know, he had the most time to acquire friends. Whoever, you know, it was called the first mover advantage, the first kid on the block, whatever you want to call it. But the idea is that those who came first, you know, as time goes on, they will acquire more and more friends because, you know, they had many more friends at the beginning. So the problem is that this type of model never gives a chance to a latecomer. It would never allow you to have a new kid coming in and become very popular in a short time. But it would never allow for a web page to come in and become very, very popular in a very short time frame. But we know that's not the case. We know examples on the World Wide Web where pages came late and yet became very highly connected. And the best example is Google itself. Google was a relatively latecomer to the game. I remember that in 1999, I was at the conference in California, and one of the Google founders came in, and he had a big box of T-shirts with him, with the Google sign of it, and was giving it to everybody. So, hey, there is this search engine. Go ahead and try it out. So I still have that T-shirt, essentially, with the Google sign of it that Sergey Brin gave me. So Google is an example of a web page that came relatively late and yet became a major hub. So how can you come late and become a hub? Well, if you want to understand it, you have to realize that it's not only the number of friends that matter, but also what are your capabilities of making friends. In the same way, when it comes to web pages, it's not only matters how connected that web page is, but also matters what's the content. And the way to model that is to say that each node has a fitness. Fitness is your ability to make friends. What do I mean by that? If somebody meets you, will that person want to again meet you, want to see you once again? That's your fitness. Fitness is a web page. Web page's fitness is if you go to that web page, do you ever want to go back again? Or you want to forget it right away because it's completely irrelevant? So we need to modify now our preferential attachment rule and to say the likelihood that the node will grow is the product of its fitness. If it has a high fitness, it will grow fast. And how many links it has, because the number of links tells you how easy it is to find. And if you do that, you find a different picture. You find that nodes with a high fitness node can come in late, and yet in a short time become very, very highly connected. So the key by which a late node can actually grow very big has to do with the high fitness, its innate ability to acquire links. But there is an interesting prediction this model gives. So one of them, of course, is that let's run this little model. So we start with the nodes, and each node has a fitness, and the numbers tell you the order in which they arrived. And what I want to emphasize in this picture is that you will see that the biggest node will not be the first one, but will be, I guess, number 6 or 7, because it came late, but nevertheless had a high fitness, so it grew faster than anybody else once it arrived. So it is possible to come in late and become very highly connected. But this model has also a very important prediction that is not so good news sometimes. And that has to do that for some fitnesses, there are some situations where one node's fitness can be so much larger than everybody else that as the network is growing, it will capture most of the links. And this is what I'm going to show you here. You will see that the purple node came in relatively late, but it has a much higher fitness. You don't see the fitness, the color corresponds to the fitness. And you will see that as the network is growing, it will grow faster than anybody else and will become a major, major node. So there is a possibility that if somebody's fitness is much higher than everybody else, it will capture all the links and nobody will have a chance in the system. And if you think about, for example, of Microsoft and its operating system, that's one example of such a behavior, where one particular node, which is Microsoft, have captured all the users, 85% of the market, and maintained that for a very, very long time. Now, what I did so far is that I gave you examples of different types of networks. I talked about social network. I talked about the airline system. I talked about the World Wide Web. We talked, so all these examples had one thing in common. They were all man-made. That is, we created them. We created the highway system, the airline network, the World Wide Web, the internet, you name it, there was all our work. Which kind of makes you suggest that perhaps all these hubs have to do with what we do. That is, people make hubs, essentially. We have preferential attachment. We tend to like the more connected. We tend to like the stars, and we tend to connect to them. We want to meet them all the time, and that's why we have hubs everywhere. But it's not so simple, actually, in a sense that we have examples of networks that preceded us significantly, and yet they have the same property. And one such a network is within our cells. Where is a network within our cells? Well, everybody knows that the gene is the source of lots of information in our cells. And the role of the genes is to essentially generate proteins. Now, the proteins typically don't work alone, but they interact with each other. And this is what we call protein-protein interactions. Let me give an example. You know that in the bloodstream, the oxygen is being carried. The oxygen is really carried by the hemoglobin molecule, which is made of 4 different proteins that attach together, and they can carry the oxygen together. So it's a little machinery of 4 different proteins. So those 4 proteins can interact, and they form what we call protein-protein interaction network. And within each of your cells, there's a very complicated network that we call protein-protein interaction network. But there is another network there, which says that the proteins can interact with the genes. They can turn on a gene or turn off a gene, because not all genes are active anytime or in all the cells. So that's another network. And there is yet another network, which is the metabolism, the metabolic network. If any of you had a cookie in the front of the room, then right now your metabolic network is really busy to break that cookie down into the cellular components that your cell needs or may not need so much. For example, the sugar part. But nevertheless, it's the metabolic network that takes a chemical and breaks it into small pieces and turns into chemicals that are useful for the cell, the type of chemicals that the cell can actually use, because the cookies, as you eat it, actually never get into your cell. That has to be actually broken down to small pieces. So what I'm trying to say here, this is an example of a metabolic network, that there are many, many networks within our cells, and they're all equally important. Any of them broken, you are sick somehow, and we see examples of that in soon. And let me show you some examples of that. So what you see on the left is the metabolic network, the one that processes the food. What you see on the right is the protein-protein interaction network. Both of them are for a simple organism, which is called yeast, essentially, the one that kind of helps you make cookies and bread. And it's an organism that biologists like to study a lot because it has very useful properties, and it's studied in many, many biology labs. But if you look at the protein interaction network, you see that each node is a protein. 2 proteins are connected if they are known experimentally to interact with each other. And you can see that there is a hub here, there's a hub here, there's a hub down here, there, and many, many small nodes. So the protein interaction network is, at least at the level of the yeast, is a hub-dominated scale-free network. But it's not only for yeast. As of 3 years ago, we started to have the first maps for humans. That is, for humans, the proteins were mapped out who they interact with. And this hairball, what you see on the left, is the type of network that is in each of your cells. But yet, when the biologists analyzed it, it turned out that also has this scale-free property, that they are held together by a few hubs, proteins that interact with many, many other proteins. So why is this interesting? Well, you need to actually realize how amazing this particular finding is because, the internet has a 40-year history. The World Wide Web has about 20-year history. The cell has a 4 billion-year history. Yet, their architecture is identical, as if the same person would have designed the cell and the World Wide Web and the internet. So what you see is that an example of how nature and society discovers the same structure, the same architecture. They converge to the same underlying architecture. And we see the same properties from system to other systems. So this convergence is really interesting and beautiful and very, very unexpected, which raises an important question. So what? Why does it matter there are hops in the cell? Why do we care about the fact that there are hops on the internet? I mean, it's sort of nice, they are there, of course, but do they have any consequences? And to answer that, I will show you 2 examples. The first has to do with the robustness, and the second has to do with the spreading of viruses, which I'm sure many of you care about these days. So let's talk about robustness. What is the robustness? Robustness is a system's ability to work even when their components are broken. And this is a very amazing statement, because if you take my watch, and you can break any component of it, and the watch pretty much becomes useless, and nobody will be able to fix it. These days, you throw the watch away, and you get another one if it's broken. So when it comes to most human designs, if components break down, the system is not working anymore. It's gone, essentially. You have to take it to the shop if your car breaks down. Anything that is broken, you have to replace it because it's not able to function anymore. That's not true for the cell. That's not true for the internet. What do I mean by that? As I'm talking to you, there are millions of errors in my cells, and I don't notice it. I'm able to continue talking, and none of you sees that, because somehow the cell is able to take care of these problems. In the same way, we all use the internet on a daily basis, and I assume that some of you are even browsing the web right now, either on your handset or on your computer. And yet, you can do that despite the fact that at any moment, hundreds of routers, that is, these computers that pass the messages, are broken. There are measurements to show that at any moment, if you look at the internet, hundreds of routers are not functional. They may be broken for 5 minutes before they fix it. They may be broken for 2 days before somebody notices, but they're broken and they're not functioning. Yet, you never notice that. The system as a whole can continue working. So how is it possible that certain systems, like the cell, like the society, like the internet, can go on even when their components are missing? You go on vacation, and the school doesn't fall apart. Your workplace doesn't fall apart. And yet, when it comes to human designs, any component you break, you can throw out the piece, the watch or so on. And the question also, what in particular, is that could it be that the network structure helps? That could this robustness be built into the network structure? And to answer that, we can start from a little network and ask the question, what happens if some of the nodes break down? Well, what happened in this case? If the nodes break down, the network could break into small pieces. For example, as I show here, because if these 3 nodes are missing, then you cannot get from this node to that one. And this turns out to be a problem very heavily studied by both mathematicians and physicists, and goes under the name of percolation theory. What is percolation theory? It simply asks that if I have a network, it could be just simply a square lattice, the one that you have in your math books and so on, and you start removing nodes, the question is, well, how long will it take until the network will fall apart, that you cannot get from here to there because all the paths are broken, like it is shown over here. And what percolation theory tells us is that if you see what is the size of the largest clusters, what is the largest group that everybody can communicate with everybody else, and this is how many nodes I removed, if you remove a few nodes from the network, it doesn't matter. But if you remove a sufficient number, then you reach what we call a critical point, and the network will fall apart. And it's easy to understand that. If you start removing people from the people, people know each other, and there are paths between individuals, and if you start removing enough people, then suddenly these paths will start to be broken, and you can get from A to B because the middle nodes are missing. But the point is that every node has a critical point. If you remove more nodes than the critical point, the network will fall apart into tiny islands. If you are under the critical point, that is, you're not removing enough nodes, then the network is kind of connected. This, however, turns out to be true for random networks and regular networks, but not for scale-free networks. So I'm showing the same slide here that I showed you earlier, but let me show you a video. That's the best way to see it. So this is the network that we built earlier. You may remember that. And I'm going to start randomly removing the nodes. And you will see that as I'm randomly removing the nodes, the network is not falling apart. And mathematically, what we say is that the critical point of this network is exactly 1. That is, you can remove 99% of the nodes, the remaining 1% will be still hanging together. So there is some robustness built into the network that holds it together. And the best way to understand that, and is to think about the airline network. What happens if you start removing, if you start closing down, removing randomly the airports in the United States, you close it down. Well, if you choose them randomly, you most likely will be closing down the South Bend Airport. How many have you heard of the South Bend Airport here? Okay, I see a few hands up. Okay, you guys are Irish fans, aren't you? Anyway, the point is that the South Bend Airport is a small airport. If you remove it, it doesn't matter except for the people who live in South Bend or who want to travel there. You can still go from Minnesota to Chicago and to Boston and to California. It will not matter. But if you pick randomly the nodes, since there are many, many small airports, you are mostly removing the small airports because your chance of hitting a hub is very, very small because there are very few hubs. So the network will shrink but will not fall apart. And that's what we see. And actually, it's mathematically proven that this network has this extreme robustness. You can remove as many nodes you want, the remaining nodes will be hanging together. But there is a price you pay for that. What if you are not removing randomly the nodes, but you go on an attack mode? Let's start with the biggest node, then take the next biggest node down, and so on. And that's what I'm going to show you here. And not surprisingly, the network will very rapidly fall apart. Because what happens if you close down Chicago, the New York airport, Denver, Atlanta? Well, obviously, you cannot go anywhere because anytime you travel somewhere, you are going through these hubs. So you see, let me just compare these. Here we removed 27 nodes from the same network, and the network is still holding together. Here we removed 15, and it's already broken into tiny pieces. The difference is we removed the hubs. So this is why hubs matter. The hubs hold the whole network together. In the moment you knock them out, the network will actually very, very rapidly fall apart. And we have actually done the same experiments on the internet map, and we found essentially the same behavior, that if you randomly the nodes break down, the routers break down, it doesn't matter because you can still get from anywhere to anywhere. If somebody, however, is clever enough to attack the hubs of the internet, then you can very easily destroy the network. And the proof for that is on this slide, but let's not kind of go into the details of that. Let me kind of go to the last kind of application of this problem, and that has to do with how ideas and viruses spread on networks. So let's talk about the problem first. So we have, for example, the social network, and the social network tells us who is knowing whom, who gets in contact with whom. And that network is responsible for many processes. If you have a great idea, you tell your friends, they tell their friends, and so ideas can spread on the social network. But so will influenza. So essentially, if you have influenza, you come close to your friend, obviously he or she will have a chance to get it. And any type of virus that spread from person to person is typically spreading through social contact. So the question is, how do we describe this process? And the answer is that epidemiologists for a very, very, very long time have actually developed methods to describe how anything spreads. Any virus could actually spread on the network, but the same thing applies to ideas. And the idea is that the virus has a certain ability to spread, which is called often the spreading rate or virulence. What is the spreading rate? It's for example, for a influenza virus, what's the likelihood that if you and I come together, you will actually get the disease? So you may not get it, but for some cases you get it. So what's the likelihood that I will pass it on to you? And for an idea, what's the likelihood that if I tell you about that idea, you will remember it an hour later, and you will feel like passing on to somebody? So that's the virulence of the idea or a disease. And what epidemiologists told us is that the virulence of a virus matters a lot, the spreading rate, because if a virus spreads, it's very difficult to spread it. It's very hard to pass on. You know, I would have to talk to you for an hour very, very closely in order to pass on the influenza virus. Then the virus will die out. So this is how many people get infected. This is the virulence of the virus, or the spreading rate. And as long as you are under the threshold, that is, you are hard enough to spread, the virus will die out in the society, because you will get cured before you could pass it on to somebody, if it's really hard to pass it on. However, if the virulence is over a certain threshold, then it will actually spread and reach a large number of people. Why does it matter? Because the way you defend yourself from viruses is that you try to make the virus more and more difficult to spread. So for example, when it comes to the recent swine flu, then the recommendation is wash your hands. That partly protects you, but also protects the society, because it makes harder the virus to spread. So the idea is that if you wash your hands, and if you don't come in too many contacts with other people by going to lectures like this, for example, then you know, the spreading rate of the virus will decrease. And if you decrease sufficiently the spreading rate, you put it under the threshold, and people will get cured before they actually can pass it on to somebody else. So that's the basic idea of epidemiology. You stop the virus by lowering its rate of spreading. The problem is that this is certainly true if the society would be a random network, but it's not. It is dominated by hubs. It's scale-free networks. So Alessandro Vespignano and Romualdo Pastor-Satoras have shown in 2001 that if the network is scale-free, that there are hubs there, then this critical point is exactly 0 for any virus. What does it mean? Even very weakly virulent viruses could spread and reach a very large number of people. And the best example is actually AIDS. AIDS is very hard to spread. I mean, in order to give it to somebody, you have to have sex with them. And yet, you know, it really reached a very, very large number of individuals. And that was always a puzzle. How is it possible that it's spreading despite the fact that based on these theories, it should be dying out? And the reason for that is because it is spreading on the scale-free network. I showed you earlier that the sexual network is scale-free. There are hubs in there. Once a hub gets infected, given the large number of friends it has, even if it's hard to pass it on, it will eventually pass it on to other individuals. So the hubs play a very, very crucial role on how the diseases are actually spreading in the society. And so therefore, you know, when it comes to how you stop a pandemic, you try to avoid the hubs from being infected. And that's one of the reasons, for example, that doctors and nurses are the first to get, for example, an influenza shot, because they contact so many individuals that if you stop them from being sick, you are stopping the disease very significantly, because they have a large number of contacts during the day, potentially. Now, the last thing that normally I would like to talk to has to do with diseases, and I promise you, but I guess we're slowly running out of the time. So I will kind of do a jump here and move on towards the conclusions of this talk. And essentially, one thing that is becoming more and more important is to how do we think about diseases, about human diseases. And a new field is emerging that is often called network medicine, and it reflects the fact that when it comes to any type of diseases, when it comes to obesity, when it comes to diabetes, to cancer, and so on, what really happens is that your network in your cells break down. So this picture is kind of aiming to show that there is this network within your cell that I showed you earlier. Remember, there's a metabolic network, protein interaction network, and so on. And if that network works well, you are absolutely healthy. However, if components of this network break down, then essentially the cell will not be properly functional, and that shows up essentially as disease. So when we come to, but diseases are not independent from each other, because if a certain region of a network breaks down, it could bring many diseases with it simultaneously, and that's why we have several diseases co-occur in the population. For example, people who are obese very likely to develop diabetes, or the other way around, essentially. And so when it comes to understanding human diseases, You need to understand what is the network within the cell. You need to map out, understand its properties, but you also need to understand the social network of who is interacting with whom, who is influencing whom. So understanding and treating human diseases is really a very, very complicated network problem, and medicine is going towards more and more to look at diseases not as one gene broken, that is one drug problem, but mostly pretty much a network problem. Now, just to understand, and one of the things we often ask when it comes to scientific fields is that how different fields, how different problems compare to each other. And when it comes to network science and thinking about networks, it really comes out from a long way of thinking about complex systems. So this is not the first attempt to understand these complicated systems. And one way to understand that is to say how many, to compare different type of fields is to how many different papers have been written on a certain area, how many citations the top papers in the research area get. So what I'm going to do next is to try to kind of take you through very briefly to the major discoveries when it came to our understanding of complex systems, very, very briefly, and see how these areas stack to each other in certain ways. So kind of the whole understanding of complex systems started in the 1960s when people started to think about chaos, chaotic systems. What is chaos? It's the idea that even very simple systems can have very, very complicated behavior. If any of you have heard about the butterfly effect, the idea that the butterfly flapping its wing in Texas can actually cause a tornado somewhere in Kansas. That's what we call chaos, that very, very small changes can magnify in the society or in the system and become very big events. And the field of chaos was really introduced by a paper in 1960. And what this plot shows is that how many other scientists have noticed that paper, how many other scientists written papers that cited it. And for about 15 years, nobody has noticed it. That was the Wolf butterfly effect was discovered in 1963, and nobody has paid attention. Then around 1975, people started to discover it. And now, every year, about 300 papers are written that are related to the butterfly effect because they cite this paper. And there were some other developments as well. Each corresponds to another paper in chaos that was very important. Then in 1980s came the fractals. Have any of you heard of fractals? These are these beautiful pictures, great. So these really, really elaborate pictures essentially that show how, kind of beautiful patterns. And when they were discovered, there are a couple of basic papers essentially that are behind that. And they were all very, very, very highly cited, which means that were very, very influential in the literature. Lots of people wrote papers about that. Then in the 1990s came networks, and the question is, how does this new wave of thinking about complex system compare to the earlier ones? And what the data is indicating actually is that really a huge number of research has coagulated around thinking about networks, and the question is why? Why are so many people interested in networks, that every year or more than 800, 900 papers are written on the subject that cite the most cited papers in the area? And what is really network science? And network science is really an attempt to understand completely different type of networks that are out there in the nature, to understand simultaneously why the cell looks the way it looks, why the World Wide Web looks the way it looks, why the society looks the way it looks, using a common mathematical framework. And that's really what we're trying to achieve here. And the question is, what is new here? And what is new and exciting in this area is that despite the differences of these systems, because obviously I don't have to stand here and convince you that the cell is really different from a high school classroom. There's a huge difference between them. One components are tiny genes, the other one are students that know each other. Yet, when we look at the structure of the high school, and many people actually have mapped out full high schools, who knows whom, who is hanging out with whom in the high school. And when you look at the cell, when you look at the network, exactly the same architecture greets us. So this commonality that completely different systems have similar structure is really the new and exciting discovery here. And that's the one that really has excited many of us in sciences. And I'm just going to close this one with my list of collaborators. And I should mention that Reka Albert, the one that I wrote probably my most interesting papers, was for 2 years a postdoc here. So she actually studied, probably was in this many rooms as well. Now she's a professor at Penn State, but I had many other collaborators. Thank you very much for your attention.
I'm sure that Professor Barabási will entertain a couple of questions.
How the connectivity was modeled, but is there any way to show the strength of connections between nodes? Because if they are not the same strength, effect might be.
I think, let me just repeat the question away. It does matter how well you know somebody. We have very close friends and we have just acquaintances and we have people who met once and we forgot them right away. So how do we represent this difference? And this is not only for social networks. On the internet, different computers are connected with different bandwidths. Yes, so in the early stages in the 1990s, much of the work was only on the topology because we did not have data on the strengths. But kind of around 2003, 2004, lots of real maps started to emerge where there was actually weights on the links. So for example, we study social networks using phone data sets, who's calling whom, and we can ask how many times you called a certain person, how many minutes you spent on that. So people are studying that, and interestingly, there is a power distribution there as well when it comes to the strength. So that most links are very weak, corresponding to weak acquaintances, and a few are very, very strong. And these are not randomly placed. Typically, the strong links are part of communities, small group of people where everybody knows each other and talks a lot, and the weak links are between the communities. This is how communities connect to each other. So there's lots of interesting stuff when it comes to putting the links as well.
Is there some way to, let's say, artificially reorganize kind of like the internet so that make it less vulnerable?
Yes. So the question is to repeat it. Is there a way to artificially reorganize or redesign the internet to make it less vulnerable? Yes and no. Yes, because in principle you could say, why not? Let's build a new internet that would have not a property. Theoretically, one can design networks that are very, very robust, both failures and attacks. So you can design that will be optimal in that respect. The real problem is, do you really have control over the internet? And right now you don't, because University of Minnesota decides where it will connect to the internet. The high school decides where it will connect to the internet. So every institution decides itself where it connect, and there is no central authority to tell you, you must not connect here and you should connect there. So in that respect, the internet is what we call a self-organized network where the decision is at the node level. Just in the same way as you decide who are going to be your friends, the internet administrator at the institution decides where it's going to connect to the system. So as long as you allow the decision at the node level, you cannot control its structure. You always go into this structure. If you would impose kind of control over that, then you could do much more robust networks. And theoretically it's possible. Practically, we don't have control over it.
Okay, there are no more comments. One question way up there.
In the literature, there are too many researchers using the term complicated system and complex systems interchangeably. Even if you look at National Science Foundation's couple of documents, they will define complex systems as multiple components, multiple numerous connections, and so on. But what really defines a system to be complex, not just complicated?
That's a wonderful question. What's the difference between complex and complicated? There is a website out there that tries to define complex systems. And I think that the last time I looked at it, there were 35 different definitions of what a complex system is. So there is no generally agreed definition essentially in that respect. And it's a very good question. When does a complicated system becomes complex? And is a system complex because it's too complicated for us to understand, or there's something intrinsically different? And one definition that I personally like is that a system is complex when you act on a certain node and you can't decide by looking at the system what will be the consequence of that. So for example, if you simply say, you're going to stay home tomorrow and you can't go to your workplace, I can't decide whether it would have any consequences, what will be the consequences of that in the system. Will it spread or will it be localized and so on? In a complicated system like a car, that's a pretty complicated system. If you take out a component, the mechanic will tell you exactly what will happen as a consequence. Your car will not start, or maybe the lights will go off, or something like that. So that's where I would put it. When you have no way of predicting what will be the consequence of one particular changeless system, you certainly have a complex system. But that's my way of looking at it. There may be lots of other, as I said, if you care about it, Google the concept of definitions of complex systems, and you will find this website with the many, many definitions, and they're quite different from each other.
Okay, I think we should thank the speaker again. Thank you very much.